Hello and welcome to Calculus. So on day one, we are going to talk about prerequisite. We need to know a whole bunch of things from algebra and pre-calculus to survive calculus. The central idea of calculus is to study the change. So we are studying the change through three concepts. Calculus consists of limits, derivatives, and integrals. So you'll see me jokingly use K's instead of C's a lot, and you can also see in the title it says PreCalc instead of PreCalc. And that's the reason, because the letter K is K sound and C is T and so on. But anyway, so calculus has three parts. Limits. We'll have to take Calc 2, but you guys certainly can take Calc 2 if you want to. So Calculus 2 is mainly electrical engineering, yay, with power series and obviously computer science. So calculus consists of three parts: limits, derivatives, and integrals. And integrals will be for Calc 1, Chapter 5, but in our book 5, 6, and 7, going into Calc 2. Now, calculus is a study of change. So systems and things in nature change. We're getting older, taller, heavier, lighter. The car, as you drive, uses gas, and gas is converted into energy, loses the mass, and you're from point A to point B. And you have the velocities and acceleration and all of these kind of things. Calculus detects and measures those things. But then also energy. If you think about energy, that's going to be area under the curve, which is integration and so on. There's a lot of stuff that calculus, and technically calculus is base for pretty much everything we do. But in order to do calculus, we have to define mathematical function, because calculus is performed on functions, and very limited calculus is applied to non-functions. So we have to actually go back into pre-calculus and do the detailed review of things that we need from pre-calculus to survive calculus. Generally, you had those pre-calculus problems, which were your homework and exams and so on. Those become now margin work, something you jot down as a first step to move on and actually do calculus. So what are these most important things? Well, number one is the definition of a function. If you are not able to separate functions from non-functions, you might not be able to apply calculus at all. For instance, equation of a circle is not a function. You can integrate it, but you can't. You can differentiate, but you can't integrate. So we have to know in which case it's appropriate to calculus and in which cases you can't. So we start with the definition of a function. And it says function is a rule which assigns to each x in the domain a unique y in the range. And I am going to underline a few words. The word rule, domain, range, and the word unique is going to be underlined twice. Oh, the network. Thank you. Oh, come on. Really? On the first day? Thank you. Don't you love this? Is the stream working or no? Yeah, this is why we need to have someone to watch the stream in class to tell me if the stream dies. Definitely the projector stopped working, which is the issue when the network dies. So let's see if I can fix this quickly. The stream seems fine. Can you check the stream, Ali, see if it's working? Thank you. The projector is definitely not working, so I'll have to... Oh! Alright, there was a hiccup. Alright, good. Alright, thank you. So we have the definition of the function. Function is a rule which assigns to each x in the domain a unique y in the range. And underlined words are rule, domain, range, and unique is underlined twice. So now, why is this so? What is the rule? Rule is the formula you have. So whatever formula is provided with whatever amount of variables and constants and everything else, that is what we call a rule. And generally you can read a sentence and write mathematical rule reading that sentence. Melissa has $5 more than Jake. Okay, J plus 5 equals M. It's a rule, right? So rule is going to be something that is a mathematical equation formula of some kind. You have the conversion from one type of temperature to another. And mass, I mean, all of physics, chemistry, everything else. As soon as you see an equation, it's mathematical equation, no matter which science it falls in. Could be also in economics, it could be in engineering. It doesn't matter. So rule is a formula. Domain is the set of all possible input variables So set of all possible inputs, and the range, set of all outputs. Now clearly you have to have an input and you have to have a formula. You plug input in the formula and you get the output, right? And then we have the word unique, which actually makes this work. The definition without the word unique, so if you just kick that one word out, this definition becomes the definition for mathematical relation, which is the broader concept. So function is more precise. So the word unique is the one that makes function, that makes that correspondence that an x makes a unique y. So 1x gives rise to 1y. You can have few graphics associated with this. For instance, the block diagram like this, where you put x in and you get y out. Or you can think about sets, where this is your domain, this is your range. You have a whole bunch of inputs in here, and those inputs are one by one mapped into the outputs. So x1, x2, x3, and so on, and then y1, y2, and so on. And the function f is the one that changes x values into y values. Notation is going to be y equals f of x. And in that notation, this is your output, which is the part of range. And this is your input, which is the domain. So as an example, if I say that f of x is equal to x squared minus 3. This is the function. I can also write y equals x squared minus 3 because y is f of x. But this notation over here is better because I see what is my independent variable, the input variable is x. So I like this notation much better than that notation. We'll be using f of x pretty much all the time rather than y. And here's the reason. If you say that y equals ax squared plus bx plus c, well, people tend to think, oh yeah, x is a variable and a, b, and c are some kind of constants, so that we can eventually have 3x squared minus 5x plus 6 and stuff like that. But who says that you have to be so limited in your thinking? I can say that a is acceleration and that's the variable, and everything else is a constant. You see? So, yeah, sure, we are used to x being a variable, but all of a sudden we change our formulas and you don't know what the variable is. But you have a bunch of letters. This is why writing f of x equals ax squared plus bx plus c, which is much different than saying f of a equals ax squared plus bx plus c. Yeah, the right-hand side looks the same, but it's not the same at all. Because on the left-hand expression over there, the function, your input variable is x. In the right one, it's a. So there's a huge advantage in writing f of x, or f of a, or f of t, or f of s, rather than just y equals. Now, the whole thing, f of t, f of a, f of whatever, is y. So that's going to be the y coordinate as you try to plot any of these things. So it's important to know that we are using f of x because f of x will determine the input variable. And then we apply calculus in terms of that variable. It's going to be the derivative in respect to x, the integral in respect to x. Or you will see the fundamental theorem of calculus eventually, which says you take the derivative in respect to x, but you integrate in respect to t, and you get right, some stuff. So you have to be able to play the game of these variables and chase what is the main variable of the problem and what are the constants and parameters and so on. Eventually in this class, we are going to distinguish between the variable, the parameter, and the constant, and all of them will have designations as letters. So when I write ax squared, this a is a parameter, this is a variable, and this is a constant. And you say, oh, but they're letters. Yeah, they are. But they serve different things, purposes in mathematics. So we are going to go and look into the details. It's a lot of OCD type of things in this course. So pay attention to the detail, and we'll do that. So that was a little bit about notation. And now, if I have f of x equal x squared minus 3, visually, if I say what's f of 2, well, clearly between these two, what I did is I replaced x with 2. The common sense is to replace x with 2 on the right-hand side and compute. So if I'm to say, well, so what's f of a heart, is going to be heart squared minus 3. It doesn't matter what we put. It could be a completely new function, which we are going to do very shortly, called function composition. It could be a number, like we just had to compute 4 minus 3 is 1. And whatever you plug in on the left, which replaces the x on the left, will have to replace all x's on the right. And that is what we say computing a function, right? So you just plug in whatever it goes there, and we get the answer. Now, using this case, because we can, I have 2, 1, ordered pair. That's your x, that's your y, that's your input, that's your output, that's your domain, that's your range. So all of these are interchangeable, and they all mean the same thing. So x is the input variable, right? It's in the domain. It's x. It's the first coordinate of every point that you get to put down. And the y is the output. And what we do is we compute enough of these, and then we connect them with a line, and we call that a graph. Please don't call the xy axis a graph. That's not a graph. That's a set of coordinate axes. It's a coordinate system. The graph is the line which represents the function which you draw on coordinate system. So if you have something like this, right, that's not a graph. That's just coordinate system. If you have this, this is a graph. So when you have x squared, I should have actually, let me just go and draw x squared minus 3. There we go. So that's your x squared minus 3. So if you just have set of coordinate axes, it's just called coordinate system, and that's it. And you have different coordinate systems, as you are going to discover in Calc 2 and beyond. And now you have just this one 2D graph with x and a y as dimensions, x dimension x and dimension y. Dimension x is input, dimension y is the output, and you have these guys together to create a coordinate system. And then with this partition, you can find any location in this two-dimensional plane, computing points, let's say -2, -1, 0, 1, and 2, will give you y values, and you can connect the dots and have the graph. So functions have input, have output, and have the rule, which is the formula, and then the uniqueness part is what actually makes a function a function. Otherwise, it's a relation if there's no uniqueness. So each x produces unique output. Let's connect that to the world around you. What's going to happen? Yeah, how sure are you? 100%. Sure I'm not going to cause the earthquake? How about start a car? Oh, see? Oh. Wow. Okay. Yeah, this one. See? Same. That's what uniqueness means. You have a function which is a formula. You plug in 3, you get a number on the other end, and then you plug in 3, and you plug in 3, and you plug in. I sound like Oprah. Just whoever plugs in 3 will get the same answer, because that's what the uniqueness is, right? Can you just have this? I just hate you so much. You get a humpback whale, you get a humpback whale, you. Anyway, so the uniqueness is the part. Now, what is the domain? Well, definitely this is a domain, right? Because I did this. I can also do this. I can use my nose. I can push with this clip, right? All of those things are in the domain. what is possible to plug in to make the system work, right? You have a square root function. Can you plug in -3? You can't, right? Because you're not going to get a real answer. You're going to get imaginary answer. So -3 is not in the domain of square root of x function because you're not getting a real answer. Well, think of a light switch. Give me one thing I can't use to excite the light switch and control the lights. Come on. A laser. Very good. What else?
The mind.
My mind?
Yeah, just thinking about it. I'd be very impressed. But
You said but. Taken. Oh, you're laughing now. We'll shut that one. Anything else you can't use or you think I can't use to excite the switch over there? We said laser. Laser is a good one. Never had laser before. I can use laser to burn it, but yeah, that won't work. Anything else?
a liquid, I guess.
A liquid. All right. I mean, under pressure maybe, but yeah, liquid generally. I'll use this as a for discipline issues. Right. The cats. Anything else? I think we have enough. You can't use moon, right? Kind of big and far away. So there are certain things that are not in the domain of us to use to press that light switch and control these lights. So that's the domain. What's the range? What's the output? Well, the only output you have, light is on, light is off, right? So binary, right? Only 2 points in the range, but that's okay, right? And then we also have this idea of uniqueness, and I already talked about it at the beginning, and that is that light switch controls the exact lights that it's hooked up to. Now, you can take your car keys, disassemble it. Where's our robotics guy over there? You disassemble the car keys, and you take the little circuit board with the battery on it, right? You take that circuit board, you take the 2 prongs off of the switch that goes towards the light, and the little button that you have here to remote start your car, the 2 wires that go to that switch, you take those off and you put them from this switch. Then when you push this switch, what is it going to do? Yeah, it's going to start your car. Is it going to turn on the lights? No. Because now you redefine the function. Now the function of that switch is to turn your car on, not to turn the lights on. And that is where the uniqueness kicks in, right? So a single input provides the single output. If you change the rules of the game, change the function, you will have different output. So I rewire that switch, and then I turn on the car or cause the earthquake or whatever, right? I can rewire the switch to do so if I want to. But once the switch is wired, yes, it's a uniquely that outcome. And that's the end of the story. It's not going to be, you know, every time different thing happens. You walk in, you just like, I don't know if I should turn that switch because I really don't know, you know. It's lights or anything else. Yes.
So when you were changing the domain before, like the things that you were actually like hitting the light switch with, you were still getting the same output.
That's okay. It says that you are not allowed to have a different outcome for the same action. The action is pressing the switch. Doesn't matter with what. I can use the finger, the elbow, the knee, the punch, whatever, right? I can pick you up and just kick you right into there. It's fine. It's going to go on or off. The uniqueness is that switch controls these lights. And input is all of the things that you can use to push the switch. That's the point. And I already started talking about, imagine if we had that type of disorder and chaos in the world where you wire it to turn the light on, so the correct wiring is done and everything is done, but every time you walk in and you push that switch, anything goes, right? You start someone's car, you start the earthquake over here, like nukes get launched, right? You don't know. That would be definition of non-function, and that is definition of non-function. That's chaos. You have it with the texting. You text, and then the autocorrect. There's no function there, all right? The autocorrect just keeps changing your words to whatever the autocorrect thinks is supposed to be there, right? Even though you clearly wanted to type back in. But you can take that one step further with texting. Imagine if there was no correlation with what you type and what shows up on the screen. So you push R and prints K. And then you push to erase that K and it prints M. And then you push to erase that M and then it prints number 2. Right? You push to erase and it finally erases, but you still have the other ones. You push erase again and it prints Z. Right? Because every time you push whatever key, whatever comes up. It would take you forever just to type in OK. Because you just try to figure out the amount of luck that you would need to type OK. And it's a nice probability problem. So, right? So, uniqueness is once the formula is written down, once the rules of the game are set, the switch is in place and whatever, right? Once you push that, or whoever pushes it, or with whatever means it's pushed, the lights either come on or off. And that's the end. That's the idea and that's the end. Now, when I push the switch, I can wire the switch for multiple lights to come on. That's fine, right? What I'm not wiring this to do is to start the car and lights at the same time, and then someone else comes in and pushes it, and it's a different outcome. So that's the idea. Once the function is there, no matter who plugs in what, the same result will happen every time. Now, generally, this is confused with the idea that, for instance, let's go with a very basic f of x equals x squared. And then you might say, well, f of 2 is 4, and f of negative 2 is also 4. Yeah, but this is true, and this does not violate our definition at all. It says each input has its unique output. So, number 2 will always give 4. That's all we care about. So anytime you plug in 2 in x squared, you are going to get 4. That's what we care about. I don't care how many other things will also produce 4. Remember, I push the light switch once, and 16 of these come up, right? That means that this one light switch, right, gave rise to all the, because they're all connected, right? But then you also have a 3-way switches in your house, right? So on one end of the hallway, and on the other end of the hallway, and you click on one end, the light comes up, you go to the other end, you click again, and the same lights turn off. That's exactly this, actually. That's this part, where the beginning of the hallway is, let's say, 2 feet, and then away from the middle of the hallway, and the other one is negative 2 feet for purposes of, right? So you click one switch, and the lights, 4 lights come up, and you go to the other end, you click, and those 4 lights go off. There you go, right? So it doesn't violate the definition of a function at all. And also, negative 2 always gives 4. Now, what's bad? Meaning not a function. I mean, it's not bad or terrible in terms that, you know, it's unusable because you have circle, it's right there, right? And all these lights and stuff, it's a lot of circular stuff. So what's not a function is that if you go and you say, plug in 2, and you get, let's say, 4 and negative 4. Now, that is not okay. It is not okay to get 2 different outputs for a single input. That's no bueno. Now, we can show that in a diagram where a single x1 gives 2 different outputs. So this is domain, and this is range, and 1x is going to give 2 y's. That's not good. Now, we see that with, let's say, x equals y squared. That one is not good, because if my x is 4 equals to y squared, okay, this is an annoying thing. I don't know if you noticed what happened. This y squared disappeared as I was writing this line. For whatever reason, that happens sometimes. So if you see that something disappeared and I didn't catch it, let me know so I can fill it back in. Right? Did anyone notice that? Hand up. You were not. So as I said, I wrote this down, and then I was writing this line, and as I was writing this line, this just disappeared. So that happens sometimes, and if you catch it, let me know so I can fill it. If I don't, see, there it disappeared again. And it's actually syncing issues between the cloud and this, so when it doesn't, right, network and all that kind of stuff. So, yeah. All right, so what happens here now? I am going to take square root of both sides, but as I take square roots of both sides, I have to put plus minus. And there you go. So plus minus 2 is equal to y, and your single x equals 4, produced, oh, come on, produced positive 2 and negative 2 on the y scale. I have no clue where I am right now. So this was x. Why is it triple over here now? So I said plug in 4, y squared, and then take a square root. All right, good. Okay. So this is what we have for our notion where something is not a function. We use vertical line test for visual confirmation that something is a function. The relation is a function. And the way we do that is we draw vertical lines. So if you have a graph, like we had earlier, the graph of this one, -3. If you draw vertical lines, you see that these vertical lines cut through this graph function exactly once. Well, that means each single x that we drew the vertical line through produces a single output y. So it's a function. So this is your f of x equals x cubed minus 3. But if you have the sideways one, which was your x equals y squared, when you draw vertical lines now, you see that for each x, you have 2 outputs here. So this is not a function. Because a single input x returns y1 and y2, as we see in the calculation over there. When I plug in 4, I get -2 and +2. So yes, it's a function, and no, it's not a function when it fails vertical line test. So now what is another example of this? A circle. I spent a long time making sure I can draw a perfect circle. So I'll show off my skills. Come on. I'm telling you, I'm really good. So this is a circle with radius 3, say. And clearly, you draw these vertical lines, it fails. It fails vertical line test. Now, what is the equation for a circle? Anyone? Equals, over there I have 3. R squared, right? Which is 9, in our case. Not a function. So, do we see something happening? Right? So in general, if you are staring at the formulas, y to even exponent, not a function. Y to the odd exponent, yes. So if you had the y cubed, when you take cube root of both sides, you do not put plus minus, or y to the 5th, or y to the 7th. But if you have y squared, y to the 4, y, all give rise to plus minus situation, and then it's not a function. So generally that's, I mean, there are more in-depth things that we are going to discover, but this is the one that is really obvious. And you should know it now. We are going to cover this more in depth with those weird situations when we get into chapter 3 to work out on implicit differentiation, where we are taking derivatives of non-functions, in which case you are going to see other things that would be there. Also trig, if you think about trig, trig functions are fine, but the non-restricted domain inverse trig functions are not fine. They're not inverse functions. They're inverses, but not inverse functions. So we'll talk about that actually now, soon. So this is the basic idea of a function. Uniqueness has to be observed. You have input and domain, output, range, and you have some kind of formula to work with all of those things together, right? And then you get into this part of graphing. Well, actually, so the types of functions you know first. Let's take a look at the types of functions first. So these are the types of functions you guys know, and we start with a polynomial, which is going to be, let's say, p of x polynomial, right? a0 plus a1x plus a2x squared plus dot 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 plus an x to the n. It has to have the highest, what we call a leading term, with the highest degree. It must have it, because that's what we know. It's a, let's say, a cubic function, right? X cubed, or a quadratic. X squared is the highest. So it has to have the highest. Now, this is the general formula for all polynomials, to whatever amount of power you need to go to. And you see it's, this is a constant function. Then if you have these two, it's a linear, y equal mx plus b. Your a1 is m, so mx plus b. And here's your quadratic, ax squared plus bx plus c, right? You just read it backwards. So all of those are encoded into what we have here. So these are all polynomials, and this is technically chapter 2 of your pre-calculus. You know to find the roots and synthetic division and the rational zero theorem and all of those kind of things. That all of that knowledge of chapter 2 is now assumed under that one statement. Then you have your exponential function. Let's say f of x equals a to the x. This is where your e to the x is and all of the other stuff with all of those problems from chapter 3. So exponential function, right? Then you have the logarithmic function, where f of x is equal to log a of x. Another, we'll talk about logarithmic functions in detail. Again, chapter 3 has a lot of these cool highlights. We have the rational function. Should have done this earlier. R of x is going to be p of x divided by q of x. These two puppies are polynomials. So we have the ratio of these. You have a rational function. Well, that's the square root, capital R of x, whatever. Square root of some function. You know, put the polynomial in there or exponential or whatever. It's a square root function. I don't like to call it absolute value function, but all right, fine. So absolute value, a of x, whatever, is a of f of x. This is more of a function composition, but whatever, we can keep it there. Oh, trig. Yeah, we have a whole bunch of these things. Y equals sine x, y equals cosine x, y equals tangent x, and then y equals cosecant x, y equals secant x, and y equals cotangent x. If you have used in previous education arc sine, arc cosine, just use it. That's fine. I'm for inverses. You know, if you have that, because inverse functions are also there as y equal inverse x, and then some of you might know it as arc sine x. So use it whatever, and then plus other 5. I want to list them all. What am I missing? I think that's it for the basic ones. You learn hyperbolic functions in Calc 2. So, yeah, I might have everything for now. Good. By the way, what you see here is a drop in a sea. There is a book, 2,500 pages by Abramovich. 2,500 pages on functions. Polynomials take half a page. So, all right. So, yeah. So those are types of functions. And now we can graph them. And now you know that you do not have graphing calculator on your exam. That is, you can bring solar calculator with basic operations. You can bring the scientific one, but no graphing calculators. That means that graphing, basic graphing needs to be known. Now, the most simplest idea here is that all of graphing across all of the functions ever, doesn't matter whether you learn it in the first grade or Calc 2, all of them you can graph by simply plugging in x's that you choose, obtaining y's, and connecting the dots like in a coloring book. It's a very, you don't have to color. So you can obtain any graph by simply choosing x values, computing y's, plotting the points, connecting the points, and call it a day. It's very inefficient, but it does the job 100% of the time. The alternatives to this, right? Anytime you don't want to be annoyed, you learn extra things, which means you know the way basic functions look like. For instance, if I need to graph quickly y equals 3 over x plus 5, say that's the function that I have to work with. The way I do this is I realize y equals 1 over x is the default case. It's a rational function, and I know, I memorized its shape. And then I use section 1.6 from our current pre-calculus textbook with a chili pepper on top, right? To move this function around to fit what I need. So if I am able to extract the base shape out of what was a mess, I am able to sketch the graph quickly. Now, the rules in so this is a PreCalc 1.6 section. You can go to the tutoring center or the library, take the book out, take a few pictures and review it, or you can find lectures online. This section deals with transformations of functions. And what you can do is you can add a constant or subtract a constant from a function to move it up, down. Maybe I should do this red so it stands out. So you can take the function, add or subtract a constant which will move the function up, down. You can add, subtract constant c directly on x, which will move it left or right. Plus is left, minus is right. You can multiply function by the constant, which will give you the vertical stretch or shrink. You can multiply inside to give you horizontal stretch or shrink, and then you can reflect on x-axis and reflect on y. And that's it. These 6 transformations that work on the graph. So now, what do I have? I have y equals, what else? 3 over x plus 5. By the way, every single lecture that I give is, I don't have notes or anything like that. I just go. So every lecture that I give is different. And if you need to hear the same lecture in a different light, you just look up for my older Calculus 1 lecture on the same topic. Because every time I just make up examples as I go, and the order and everything else. So you might have some different perspectives by watching other. Anyway, so now I'm looking at this and I go, okay, so this is 3 times 1 over x plus 5. So I definitely have CF, and I definitely have f of x plus 5. You see? So this is how I decompose it in my head when I'm looking at the problem. I know that this 3 multiplies the entire function, so that's going to be the vertical stretch because it's bigger than 1, right? If you multiply by half, it cuts it shorter. And then I have the x plus 5 over there. X plus 5, it's a direct modification on x, and that direct modification on x is the one that shifts it to the left because it's plus 5. So now, I know that 1 over x, I memorized this, and I'll give you all of these now so you can enjoy your week. if 1 over x is the basic shape with the horizontal and vertical asymptotes where the x and y axes are, I know that the function needs to shift 5 units to the left because it's plus 5. So I'm going to draw 1, 2, 3, 4, -5. And now this times 3 will just make it taller, but we really can't do a great job with that, so I'm just going to draw closer to the x-axis so it kind of falls faster, rises faster, and all that kind of stuff. And this is the y-axis, and this is the x-axis, and this is where -5 is. And there it is. That's the quick sketch. So we deal with all functions this way. We disassemble it in its default state, and once it's in this default state, we can just shift it left, right, up, down, reflect, and all of that kind of stuff. So I'm going to do one more example of this, and then we're going to talk about absolute values because those are generally tricky. So another example would be, actually try this on in your seats first. Talk to people whose name you already know. Right? Right. Y equals e to the x minus 2 plus 1. So this is a standard pre-calculus. You're going to see e so much in this class, you'll be sick of it. That and polynomials and trig. Let's see if anyone knows. Ooh. Good. Right, let's take a look. So what's the base function? What's the base function? Exponential, e to the x. And the base function looks like this, right? Now, I have 1 up, 2 right. So, what used to be here has to go 1 up and 2 to the right. The horizontal asymptote also has to go 1 up because everything goes 1 up. Yeah. And we just draw this through 2, 2. So these quick sketches, right, that need to happen instantly as these functions are written down. 2c, right? We're going to deal with different types of functions when we have to draw in calculus in chapter 4, like e to the sine x or something like that. So we have to build up to that, but we need to know the basic stuff from PreCalc so we can build up to more interesting things later. Another thing was the issue with the absolute value. Absolute value function is just y equal absolute value of x, which is defined x for all x is bigger than 0, and negative x for all x is less than 0. Oops. Less than 0. And it produces the basic graph that's like a V. It's a 45 degree on each side. But this is not even, you know, the beginning of the story for absolute value function. What you have with absolute value functions, you can plug in anything in here. And as long as you are clear with what absolute value does, you should not have issues in graphing anything. Can anyone tell me what is the purpose of absolute value function? What is it? Essentially, what is it? What is it? Yes.
How far it is from 0?
9. What? How far is from 0? What?
How far the x is from 0?
Yes, the number at 0. So it's not makes things positive. That's a consequence. Absolute value function measures the distance between the point and the origin. That's what it does. So if you think about -3, -3 is 1, 2, 3 hops away from 0. So it's a positive number. So when you say absolute value of -3 is 3, these are different 3's. Right? And it's not in the sense that 1, 3 is negative, 1 is positive. It's in the sense that one of these is a location on the graph and the other one is distance from that location to 0. If you draw 0, 1, 2, 3, 1, 2, 3 hops, and you say absolute value of 3 equals 3, these are still different 3's. Yeah, I know 3 equals 3. Sure. I'm not going to debate that. Conceptually, they're different 3's. Would you agree that 2 p.m. and $2 are both 2's? Yeah, they are, right? But are they? No, right? There you go, right there. The 3 inside the absolute value is the location in space on the number line. The 3 on the other side is the distance between that location and the origin. So when you write it on a side like this, yeah, sure, it appears that absolute value just makes everything positive and you go away, right? You walk away. But conceptually, when you really dig in, and if you want to know math, and some of you definitely do, this is not the same thing. Just like $2 is not the same as 2 p.m. They both have 2's, right? So that's the essence. It measures the distance. But now you can also embrace the idea it makes all y's positive. And as soon as you get that in your head, the graph that I had over here, combined with this function and the one that does not have the absolute value, immediately all connects, I hope. Y equals x, graphs this way, y equals absolute value of x, graphs this way. Do we all see that this part of the graph was bounced up? Because these y's over here are negative. And all we did is made those y's positive using absolute value, and that's why they bounced up. So now, armed with this knowledge, y equals sine x is your, let's do just one principle, is your wave that looks like this. So what is y equal absolute sine x? It's a common sense. Yeah, just the top bumps. All of the bumps will be above x-axis. So the graph for this is hop, hop, right? Come on. I'm waiting for the projector now to kick in. There we go. Good. So any graph that goes underneath the x-axis will pop up. So in this case, again, this was negative, bumped up here. This was negative, bumped up. That's the essence of graphing absolute value functions. So you do the graph ignoring the absolute value and then bump above x-axis whatever ended up below. Very simple. Well, you can practice on this one here. Y equals ln x. We all know what that looks like, right? It looks like this, going through 1. What is y equals absolute ln x? So draw that one.
Talk to others, you can hold them.
All right, so we start with 1. That part is above x-axis, so that stays the same. The one that was below is just going to get bumped up, and it creates this spike at 1. We all have that? Good. I hope you're not disappointed. That's it. That's the way you graph absolute value function.
So is it an exact reflection?
Yeah. Because all of the negative y values become positive y values on the same x location. Actually, you know, where I went to high school, there was no party time, unfortunately. It was all, you take the ruler and the compass and you have to actually do these graphs to show that that's true. So what you do is you have the 45-degree line like this, then you have this point, and that point reflects here, and then this point is 2 units, goes there, get 3 units, goes here, you draw then line this way. Now obviously all of that has to be done with a ruler, and if you don't have the square notebook, you're not allowed in classroom. They tell you go out, play ball, school is not for you. It's, yeah, I have so many soccer days, you have no idea. You forget a pencil or eraser or notebook, you just, yeah. And yeah, so you quickly see, you know, the way they connect, and it's exact reflections. You just sit there and do one by one like that. And that's for all, for trig, for exponential, for logarithmic, for, right, to find their absolute value. So you just, you know, sit and play with it, and eventually it works out. Good. So we dealt with graphing, we dealt with this, and now we can finally talk about break, or you're good? Break? All right, fine. I can see desperation. So we will have part 2.